In the realm of education, data is abundant. We collect information on student performance, teacher effectiveness, and school resources. But raw data alone doesn't tell the whole story. To extract meaningful insights and make informed decisions, we turn to inferential statistics. Inferential statistics enable us to go beyond describing what we observe in a sample and make inferences about a larger population. Imagine we want to understand the impact of a new teaching method on student engagement. Instead of studying every student in the school, we might select a representative sample. By analysing the data from this sample, inferential statistics allow us to draw conclusions about the effectiveness of the teaching method for all students. This is the power of inferential statistics, to generalize from a small group to a larger one. Through hypothesis testing, confidence intervals, and other techniques, inferential statistics provide a framework for making informed decisions based on data. This is crucial in education, where every decision impacts the lives of students. Within the toolbox of inferential statistics, correlation analysis stands out as a powerful technique for uncovering relationships between variables. Correlation helps us understand how changes in one variable relate to changes in another. For instance, is there a connection between the number of hours students spend studying and their exam scores? Do students who perform well in math also excel in science? Correlation analysis provides a way to quantify these relationships. By calculating correlation coefficients, we can determine the strength and direction of the association between variables. A positive correlation indicates that as one variable increases, the other tends to increase as well. Conversely, a negative correlation suggests that as one variable rises, the other tends to fall. Understanding these relationships is essential for educators to identify factors that contribute to student success and design interventions to support those who are struggling. One of the most widely used correlation coefficients is the Pearson correlation coefficient, denoted by the letter R. This coefficient measures the strength and direction of the linear relationship between two continuous variables. A perfect positive linear relationship, where the data points fall precisely on a straight line with a positive slope, yields a Pearson correlation coefficient of +1. Conversely, a perfect negative linear relationship results in a coefficient of -1. A coefficient of 0 indicates no linear relationship between the variables. Values between -1 and +1 represent varying degrees of linear association. For example, we might use the Pearson correlation coefficient to examine the relationship between students' scores on a standardized math test and their final grades in an algebra course. A strong positive correlation would suggest that students who score well on the standardized test tend to perform well in the algebra course as well. Section 4. Spearman, rank correlation. Navigating ordinal data. While the Pearson correlation coefficient is suitable for continuous data, it may not be appropriate for ordinal data, where variables are ranked in order, but the differences between ranks are not necessarily equal. For instance, imagine a survey where students rate their level of agreement with statements on a scale from 1 to 5. The difference between strongly agree and agree may not be the same as the difference between agree and neutral. In such cases, the Spearman rank correlation coefficient denoted by the Greek letter R, RHO, is a more suitable measure of association. Instead of using the actual values of the variables, the Spearman correlation coefficient ranks the data and calculates the correlation between the ranks. This makes it a robust measure for ordinal data and even for continuous data that violates the assumptions of the Pearson correlation. Section 5. Correlation in Action. Illuminating educational insights. Correlation analysis has numerous applications in educational research and practice. For example, researchers might use correlation to investigate the relationship between class size and student achievement. Do smaller class sizes lead to better academic outcomes? Teacher qualifications and student performance. Are students of more experienced or highly qualified teachers more likely to succeed? Student engagement and dropout rates. Do students who are more engaged in school have a lower likelihood of dropping out? By understanding these relationships, educators can make data-informed decisions to improve student outcomes. For instance, if a strong negative correlation is found between student absenteeism and academic performance, schools might implement interventions to improve attendance rates.